Here are solutions to homework set number 7 for ECE 463-663 Modern Control. This homework set looks at servo compensators. Now the first problem is, given a ball and beam system, I've got a beam with a torque on it, got a ball rolling on it back and forth. Find the torque on the beam to force the ball to go to a certain set point. Now problem 1 is, give the dynamics. So this is back from homework set number 4. We came up with these dynamics. Here's your A matrix, here's your B matrix. Come up with feedback gains to track a constant set point. Now one approach, what we've done before, is use full state feedback. With full state feedback, here's what the simulation looks like. I've got my feedback gains Kx and Kr. I apply those as U equals Kr times reference minus Kx times X. And for the nominal case, that ought to work. So if I try that for the nominal case, so here's my ball and beam system. Let her rip. Here's my set point, it's at +1. Tell the ball to go to +1. It does. Tell it to go to -1. Apply torque, tilts the beam, ball rolls left. Eventually catch it at -1. Okay, that's the nominal case. Well, what happens if the model is wrong? What happens if instead of the ball having a mass of 3 kilograms, it is 3.5 kilograms? So use the same control law, but now the mass is actually different than what I expect. I tell it to go to 1, and it just rolls off. Okay, so that didn't work. Suppose instead the ball was slightly lighter. Let's make it 2.8 kilograms. Now when I try it, there's a constant disturbance. I expect the torque to be force times distance. If the mass is a little bit less, it looks like a disturbance on the beam. Where that shows up is I tell it to go to 1 or -1, and I miss. There's the steady state error caused by the constant disturbance. So that's the problem with full state feedback. It cannot handle a constant disturbance. In this case, it also doesn't really track a constant set point if you change the dynamics. To get around that, add a servo compensator. What the servo compensator does is it integrates the difference between the set point and the output. That gives me a 5th state. I've got 4 states for the plant, 1 for the servo, gives you 5. I will find my 5 feedback gains. What the feedback gains do is they stabilize the closed loop system. When stable, if I have a constant set point, I know that all the states go to a constant. If z is a constant, then z dot is 0, meaning that y goes to r. That's in spite of a constant disturbance or a constant set point. So to do that, I create the augmented system. Here's the augmented A matrix, augmented B matrix. Find the feedback gains to stabilize the augmented system. In MATLAB, it's create the augmented system. I call that A5. The augmented B matrix. Now use pole placement to place 5 poles. Here's my dominant pole. That's set by the requirements. And the other 3 poles, put them someplace kind of arbitrary, 2, 3, 4. So here's Kx, or K5. First 4 gains are Kx. Last gain is Kz. Now let's try it. If I try it on the linearized system, here's your A minus BKX, BKR. Everything works in the linear system. Does it work on the nonlinear system? That's the real test. So go to the nonlinear system. I'm going to change the feedback control law. So this is what I calculated. Here's your Kx, Kz. Here's my servo. Z dot equals 0, integrator, plus BZ. Pole at 0, controllable, the servo state. Change the control law. So now I'm going to feedback minus Kz times Z minus Kx times X. Add the servo compensator. Integrate the servo compensator. And now what it should do is track. If I take my nominal case, when this is 3 kilograms, it should track a constant set point just fine. That's not all that impressive because the previous control law, full state feedback, also tracked a constant set point in the nominal case. So far, I'm not all that impressed. If I change the system, let's make the mass 2.8 kilograms. See what happens. Now when the mass is a little bit lighter, I have less torque on it. Torque is force times distance, less mass, less force, less torque. The servo compensator compensates for that. The integrator tries to figure out what input do I need, what constant holds the output, holds the error at 0. And at 2.8 kilograms, it figures it out. Works great. Let's go back and try 3.5 kilograms. Now that was unstable previously. If it's 3.5 kilograms, again, that's the integrator trying to figure out what do I need, what torque do I need to hold the output. It eventually figures it out, forces the steady state error to 0. That's what the servo compensator does for you. Now a problem with the servo compensator is, let's go back to the nominal case. It works for constant set point. It doesn't work for sinusoidal set point. So suppose I did this. Can I track a sine wave? Well, it does track a constant, but it's not designed for sine waves. It cannot track a sine wave. So tell it to track a sine wave. It's trying to figure out what constant do I need to hold the output at the set point. Well, the input that I need isn't a constant. So it's trying, missing. Doesn't work for sinusoidal inputs. How do you track a sine wave input? Well, that's the last problem on the homework. If I can find it. Okay, where'd you go? There you are. So with the servo compensator, works the linear system, works on the nonlinear system. If I have a sinusoidal set point, modify it slightly. Change the servo compensator so this has poles at the set point or disturbance. So this will be plus minus j 1/2. And make it controllable. I now have 4 poles for the plant, 2 for the servo, gives you 6 feedback gains. There's your K6. The first 4 gains are Kx, last 2 gains are Kz. So form the augmented system, just like before. Close the feedback loop. Define K6. I define servo. This has poles at plus minus j.5 and is controllable. Here's my augmented system. Here's the A matrix, zeros matrix, BZ times C and AZ. The B matrix with respect to R, B matrix with respect to U. Pole placement. Place the dominant pole and the other poles. Kind of arbitrary where you put them, that's where I chose. First 4 gains are Kx. Last 2 gains are Kz. When I say arbitrary, I want to keep the gains small, but I want it to be stable. I don't really know where to put the gains. That's the problem with pole placement. But wherever I choose, it can find the gains to put you there. If I try that on the linear system, so here's the closed loop A matrix, B matrix with respect to R. I need to use our step 3 function that we created with time points, an initial condition is 0, and my set points is a sine wave. It'll track it. So here's R, and here's Y. It tracks the constant set or sinusoidal set point. Now the linear system, everything works in the linear system. Does it work on the nonlinear system? So to do that, what I will do is take the feedback gains that I calculated, change my control law. So here's the Kx, Kz. My servo now has poles at plus minus j.5, controllable. I have 2 servo states. Now when tracking a sinusoidal set point, here's what it looks like. Let it go, there's my set point going back and forth. The control law is trying to figure out what the input needs to be. I know it's a sine wave at 0.5 radians per second. It's trying to figure out the sine and cosine terms to cause it to track. And eventually it locks on. Bang, got it. If I change the dynamics, I suppose the ball is actually 3.5 kilograms. Can it still track it? So there's my set point. It's trying to figure out what the input needs to be, sine and cosine. The solution is different because it's a different system, different mass. Eventually, doesn't quite figure it out. There's a DC term is missing out. Sort of follows it. Try slightly lighter. So it is tracking the 0.5 radian per second component. It has a DC offset though. If I want to track a DC term and a sine wave term, that's a different problem. I now need a supercompensator with 3 sets of poles. One at 0, the other 2 at plus minus 0.5. In this case, it looks like it's tracking. Just for fun, what happens if I have a step input? So this is designed to track a sine wave. Change the input to be a step, and it's not designed for step input. It works really, really bad. If one is to track a step input, go back to the previous problem. Sine wave input, this problem. Either type of input, that's not covered on the homework. You might see that on the next test though. So anyway, that is homework set number 7 for 463 Modern Control, servo compensators.